Hi, so today we will be starting a very new chapter which is oscillations from your plus 1 physics, correct? So when you start itself, the first thing that you need to know is that oscillations is a very simple chapter and you need not have any prerequisite knowledge of any other chapters in order to study this chapter which is oscillations. At first let us study two terms from this chapter which is periodic motion and oscillatory motion. First one is periodic motion and the second one is oscillatory motion. See, let's see what is a periodic motion. See, the name itself says that if anything repeats over a period, it can be called as periodic motion, or I can say that any motion that repeats over itself in a particular time period is called periodic motion. See, we know that there are many type of motions that we see around us. One of such an example is planetary motion. Here we see satellites revolving around the planet or planets revolving around its own stars. So all these are examples for periodic motion. So for any motion to be classified as periodic motion, they need to satisfy only one condition, which is that it should have a regular time period. So any motion that have got a regular time period or a motion which is repeating over itself in a regular time period is called periodic motion. Whereas now see, both of these are examples for periodic motion. Here you are having planetary motion or this see solar system, even the second hand or minute hand or hour hand of a clock, all these are examples for periodic motion. In every 60 seconds your second hand completes one rotation, correct? The same happens with minute hand as well as hour hand also. Okay, so this is called periodic motion. The only criterion is that it should have a regular time period. Okay. Now let us see what is oscillatory motion. What is oscillatory motion? See, oscillatory motion is a to and fro motion. In periodic motion you had the complete coverage of a circle or the entire path was covered. Here what happens is that it will be a to and fro motion with respect to a particular position. See, if this is the position that you consider as your mean position, you will be having a positive extreme, mean position and negative extreme. So what is oscillatory motion? Oscillatory motion is a to and fro motion. Oscillatory motion is a to and fro motion with respect to a mean position. See, what was the difference between periodic motion and oscillatory motion? In periodic motion you had the complete coverage of a circle, whereas in oscillatory motion it will be a to and fro motion and you are having particular specific positions in oscillatory motion, which are positive extreme, negative extreme and mean position, right? Now you can say that all oscillatory motions are periodic in nature. What is the reason? Because all oscillatory motions are having a regular time period, but you can never say that, you cannot say that all oscillatory motions, all periodic motions are oscillatory. See, all periodic motions need not be oscillatory, all periodic motions need not be a to and fro motion, but all oscillatory motions should have a regular time period. So you can say that all oscillatory motions are periodic in nature, but all periodic motions need not be oscillatory in nature, right? Okay, now here you are having the projection of a circle, projection of a particle which is in a circular motion along its diameter. So we are going to study the projection of a particle, okay, the projection of a particle along the circle. Now here when I consider, see, if there is a particle here and this particle is moving around the circle, if that particle moves around the circle and completes one circle in a time period and it repeats that process, then what can I call this motion? I can say this as an example for periodic motion, because in every one time period the particle is completing one circular track. So when you consider the motion of the particle along the circle, it is an example for periodic motion, right? Okay. Let's see, what do you mean by projection? You have already studied in this chapter motion in two dimension or motion in a plane. You have already studied about vectors, projection, all this, but I will say that again. See, I am drawing a vector which is vector A here. See, you can see vector A here. Vector A is having a projection along x-axis and likewise vector A is having a projection along y-axis. So what do you mean by projection? Projection is the component along x-axis or y-axis. Here the vector is A and this is the projection of vector A along x-axis, and I can call it AX. Likewise, this is the projection of vector A along y-axis, and I'll call it AY. So what do you mean by projection? Projection is nothing but the component of that vector along x-axis or y-axis. I think it's very clear, right? So projection means what? Projection is the component of a vector along x-axis and y-axis. Here I am having vector A, and vector is having its component along x-axis, which is AX, and the component along y-axis, which is AY. So I am having the projection along x-axis and y-axis as AX and AY respectively, correct? Now in this case, when you consider the motion of the particle along the circle, it is an example for periodic motion. Now I will consider the motion of the projection of the particle. See, when you consider the projection of the particle here, when you consider the projection of the particle which is currently here, see, this will be the projection along x-axis and this will be the projection along y-axis. When when the particle started from here, the entire projection or the entire vector was along x-axis and the projection along y-axis was 0. Now when your particle started moving up, what happened? The projection along x-axis started decreasing and the projection along y-axis started increasing. So when your particle started from here, the projection along x-axis kept on decreasing. So when your particle reaches here, the projection reached here, but the projection in y-axis it reached here. So what is very clearly understood is that the projection along x-axis keep on decreasing and the projection along y-axis increases. When the particle reaches here, the projection along x-axis becomes 0 and the projection along y-axis is maximum. Now when you move on to the second quadrant, the projection along y-axis again decreases. See, when the particle reaches here, projection will reach here from maximum. At that point, what is happening to our projection along x-axis? The projection of the particle along x-axis again started increasing from 0. So as you move on from first quadrant to second quadrant, the projection along x-axis further increases and the projection along y-axis decreases. Understood? And as the particle reaches here, when your particle reaches here, the projection along x-axis is maximum, but it is negative maximum, and again the projection along y-axis has become 0 here. Okay, now when your particle moves to the third quadrant, the projection which was maximum in your negative x-axis again starts decreasing and the projection along y-axis will again increase. Okay, and see, when your particle reaches here, the projection along x-axis decreases and it reaches here, but the projection along y-axis it keeps on increasing in the third quadrant. Now when your particle is reaching here, the projection along y-axis is maximum and the projection along x-axis has become 0. Now as you move on to the fourth quadrant, the projection along y-axis again decreases and the projection along x-axis increases. Now when your particle reaches here, the projection along x-axis has again become maximum and the projection along y-axis is 0. Correct? So now let's see what had happened to the projection. See, I am drawing just the projection here. Your particle actually started from here. When your particle started, projection along x-axis, I'll just say about the projection along x-axis now. See, when your particle is here, the projection along x-axis has reached here. When your particle is here, the projection along x-axis had reached here. Okay, now as you are stepping over to the second quadrant, see, the projection has become 0 and from that 0 again the projection is moving in this direction. When you reach here, projection reaches here. When you reach here, projection reaches here. See, as you are moving to the third quadrant, the projection again started decreasing. It becomes 0 here. So, and again it becomes maximum at the position when you started. Now for the same particle, for the same position, let's see what is happening to the y-axis. When you started, the projection was 0. When you started, the projection was 0. And as you kept moving higher, the projection increased. Now on reaching here, it started again decreasing. It reached 0 again at the negative maximum and again back to 0. So when you started, projection along y-axis is 0 and the projection along x-axis is maximum. As the projection along x-axis has become 0, the projection along y-axis has become maximum. Understood? So, when you consider the motion of the particle along the circle, it is an example for periodic motion. But when you consider the projection of the particle, along the diameter of the circle, along x-axis of the circle, or along y-axis of the circle, or along any diameter of the circle, it is an example for oscillatory motion. Because see, when you see this, it is very clearly understood that it is an example for a to and fro motion, right? It is an example for a to and fro motion. There is no complete coverage of a circle. It is here an example for a to and fro motion, and thus you can say that the projection of the particle along the circle is an example for oscillatory motion. Correct? Okay. Now our next point, see the same thing, it is very clearly elaborated here. See, at point 1 the projection is x1 and y1. When you reach point 2, the projection is x2 and y2 respectively along x-axis and y-axis. Now when you reach point 3, it is along x3 and y3, and when you reach position 4, it is along y4 and x4. See, here we have marked only the projection along x-axis. So you can see that it at time t equal to 0, you have started from positive extreme, and when you reach t by 4, you have reached the mean position, means projection along x-axis is 0, again it increases, again it decreases, and again it reaches the maximum. Okay, so this is the case with projection of a particle. Now we are having three basic terms here. The first one is amplitude. What do you mean by amplitude? And here you can see the figure of a swing. Okay, so a child is playing with that. So whenever you are playing in a swing, you have experienced that there is a maximum displacement for that swing. There is a maximum displacement. That maximum displacement during an oscillatory motion is called amplitude. The maximum displacement from the mean position is called amplitude. So amplitude is nothing but the maximum displacement from the mean position. See, even for a simple pendulum, when a pendulum is oscillating, the maximum displacement from the mean position is called amplitude. Okay. Now we will see the next term. It is time period. What do you mean by time period? Time period is the time taken to cover one cycle. Time period is the time taken to cover one cycle. Okay. And after that cycle, again the motion or again the path is again repeated. So the time taken to complete one cycle is called time period. Now what is frequency? Frequency is the reciprocal of time period, or I can say that it is the inverse of time period. Okay. Now let's see here. See, when you consider oscillatory motion, the first thing that comes to your mind is a simple pendulum. But actually, what is a simple pendulum? Simple pendulum is an example for simple harmonic motion. And there comes the next question, what is the difference between oscillatory motion and simple harmonic motion? See, what is the difference between oscillatory motion and simple harmonic motion? See, what do you mean by oscillatory motion? In oscillatory motion, you can say that force is directly proportional to nth power of displacement. Force is directly proportional to restoring force is directly proportional to nth power of displacement. Means, see, when you are displacing something from the mean position, the restoring force intends to come back, or you can say that the restoring force is that thing which is pulling this object back to the mean position. So as you increase the displacement, restoring force will increase. Understood? So as you increase the displacement, restoring force also will increase, and it is directly proportional to nth power of the displacement for oscillatory motion. Since the direction is opposite, see, you are pulling this away. Means what? You are pulling this away from the mean position. That is, displacement is away from the mean position, whereas restoring force is always acting towards the mean position. The tendency of the simple pendulum is always to come back to the mean position, but you are moving it away from the mean position. So you can say that displacement vector is away from the mean position, but restoring force vector is always acting towards the mean position. And that is why you are having a negative sign here. F is equal to minus kx raised to n, and here k is the constant of proportionality that you have introduced to change that proportionality sign, right? So F equal to minus kx raised to n. So this is the example for oscillatory motion. Understood? This is the example for oscillatory motion. F is equal to minus kx raised to n. Force is directly proportional to nth power of the displacement. And when you consider simple harmonic motion, see, when you consider simple harmonic motion, see, hereafter I will refer it as SHM. When you consider simple harmonic motion, your equation is force is directly proportional to first power of the displacement. Oscillatory motion, for oscillatory motion the equation was force is proportional to nth power of the displacement, but here for an SHM your equation is F proportional to x raised to 1. So here you can say that oscillatory motion is F equal to minus kx raised to n, and simple harmonic motion is F is equal to minus kx, or simple harmonic motion is the simplest form of oscillatory motion. In oscillatory motion you are having this n varying from 1 to infinity, but for simple harmonic motion n is taking the least value for an oscillatory motion possible, and that is equal to 1. And in this chapter we are dealing only with simple harmonic motion, and your equation is F is equal to minus kx. Force is directly proportional to the displacement. Restoring force is directly proportional to the displacement. F is equal to minus kx. Right? Now, in the case of a simple pendulum, see, this is the mean position. This is the mean position. For a simple pendulum, it is the mean position. And you are having a positive extreme here. See, this is positive extreme, and this is the negative extreme. This simple pendulum is oscillating to and fro. This simple pendulum is oscillating to and fro with respect to the mean position. See, a to and fro motion with respect to a mean position which is having a positive extreme, negative extreme and mean position, and the distance from mean position to positive extreme is called amplitude, which is plus a. Mean position to positive extreme is called amplitude. The distance between mean position and positive extreme is amplitude, right? Okay. Now let's see. See, you are having a simple pendulum here. See, what is the total distance covered by a simple pendulum in one time period? What is the total distance covered by a simple pendulum in one time period? So you are having one time period. What is the total distance covered by a simple pendulum in one time period? See, in one time period, your pendulum which had started from here, it will move until the positive extreme, it will come back to the mean position, it will move to the negative extreme and again come back to the mean position. So this is the total distance covered by a simple pendulum in one time period, which is equal to, see, 1a, 2a, 3a and 4a. That is from mean position to positive extreme 1a, positive extreme to mean position 2a, mean position to negative extreme 3a and negative extreme to mean position 4a. So the total distance covered is equal to 4a. The total distance covered is equal to 4a. Whereas the total displacement covered after one time period is 0, because after one time period the particle is returning back to the initial position. From wherever you started, you are returning back to the same position, and therefore you can say that though the distance covered is 4a, the displacement at the end of one time period is equal to 0. So the distance is equal to 4a and the displacement is equal to 0. Correct? Okay. Now here you are seeing three other terms. See, oscillatory motion, you know what is an oscillatory motion? F is equal to minus kx raised to n. For a simple harmonic motion, n is equal to 1 and the equation is F is equal to minus kx, and you know that the distance covered in one time period is 4a and the displacement at the end of one time period is 0, right? Now here you are having amplitude. We have already discussed what is an amplitude. You know what is the time period, and also you know what is frequency, right? Okay. Now negative sign in the equation, F is equal to minus kx. Okay, you know that See, force is equal to minus kx. Why that minus sign came? Minus sign is because displacement is always measured from the mean position. You are having a simple pendulum. See, this is your simple pendulum. And this is displacement vector. This is displacement vector, and this is restoring force vector. So here it is very clearly understood that displacement is always measured from the mean position, or displacement is always measured away from the mean position, but restoring force is acting towards the mean position. See, whichever direction you are displacing the simple pendulum away from the mean position, the tendency of the simple pendulum will be to come back to the mean position. So displacement is measured away from the mean position, restoring force vector is acting towards the mean position. So displacement and restoring force, they both are acting in the opposite direction, and that is why you are having the equation F is equal to minus kx. How did it come? F is directly proportional to x. You are introducing a constant which is k. F is equal to kx, and since the direction of both these vectors are opposite, you can say that F is equal to minus kx. Okay, F is equal to minus kx. See, before that, here itself, let's see what is the differential equation of an SHM. Okay, here you know that F is equal to minus kx is equation of an SHM. See, that is a normal equation. F is equal to minus kx is the normal equation for a simple harmonic motion. How will you write the differential equation of an SHM? Let's write the differential equation of an SHM. Okay, differential equation of an SHM. See, differential equation. We'll start with this. You know that F is equal to minus kx. But what is F? F is equal to ma. Force is equal to mass into acceleration is equal to minus. What is k? K is a constant, and k is equal to m omega square. How did it come? Omega is equal to root of omega is equal to root of k by m, or k is equal to m omega square, which is a constant. See, m is the mass and omega is the angular velocity, correct? So k equal to minus m omega square x. Now what I will do, I will cancel m, and I will get another equation which is a equal to minus omega square x. Acceleration a is equal to minus omega square x. Acceleration a is equal to minus omega square. But you know that what is acceleration when you differentiate, you are double differentiating displacement in order to get acceleration. So instead of acceleration, you can write d square x divided by dt square. So it is d square x divided by dt square is equal to minus omega square x. D square x by dt square is equal to minus omega square x. Or I'll write the final equation here, which is d square x by dt square plus, see, I'll take this minus omega square x to the opposite side and I get it as plus omega square x is equal to 0. So your answer is d square x by dt square plus omega square x is equal to 0. So you are having just two equations which are a equal to minus omega square x, and the second one d square x by dt square plus omega square x is equal to 0. And this is what you call the differential equation of an SHM. Differential equation of an SHM is d square x by dt square plus omega square x is equal to 0. You are getting all this from the basic equation F is equal to minus kx, correct?